instead of present, we just play, and then, or we can actually present. Alright, so, we're... and we're on the Guitar Bridge project, and I'm Urban Romero, Stephen Casado, Cedric Jackson, Ray Ziegler, and Casey Compatible. And so, the inherent flaw with the current vibrato bar is that you don't play one note at a time. When you play two or more notes, the intonation is lost between strings. So.
Okay, so I'm going to give you a quick useful background so you have a better idea of what we're talking about. As engineers, you all understand frequency. If a string is pulled to a certain tension, it'll vibrate at a certain frequency. So in music, we give names to those frequencies, and we call them notes. The distance between notes in hertz grows the farther up, the higher the note is. So E, like a very low E to a very low F, will be a much smaller difference than a very high E to a very high F. We measure that difference in half steps and cents. And cents are 100 cents is equal to 1 half step. And intonation is the accuracy of that interval, and that's really what our project is about, is maintaining that accuracy.
Okay, so the goal of the next few slides is to take a look at the SolidWorks models and get a better understanding of the project. The aim is to start with the big picture and then break it on down. So, to understand why our current design looks the way it does, which is on the right, and will be on the right for the next few slides, it's important to remember what the previous iterations looked like, which will be on the left. So, the assembly is nice because it will help us visualize how this project will work. Now, the bridge will sit at the bottom of the guitar, the string moves through the cams, and will run up back to the top of the guitar. On the top of the carriage, there's the cam locking tabs that you can see. They can be in the locked or open positions. The locked positions will select that string. So next up we'll have a top view, and the top view is just to really reiterate the locked versus open positions. The 3 on the left will be in the locked position, the 3 on the right will be in the open position. Next up will be the exploded view, and this is to help get acquainted with the parts and just see how it kind of comes together. There are the cams, which is A, B is the bridge bar, C is the carriage, E is the locking tabs, D is the lockers, and F is the backplate. So moving on, we have probably the most important component of the whole project, the cams. And the cams help us bend full chords. And the way it does that is with each cam has its own unique diameter, and that's because each string has its own diameter. So when you're bending a full chord of unique strings, you need to have the cams with unique diameters to compensate for the string diameters. Now, on the left is the previous iteration, which is conceivably still feasible, but would have been a nightmare to make. So we moved on to the right side. The ball end of the string will be at the bottom, that bottom hole. It will come around the top and move to the back of the guitar. What changed was the ball end of the string is now on the cam arm, which allowed us to take off a lot of material and add it to the actual cam arm, which made it easier to place the hole for the cam string, which compensates for the string tensions. Next up is the carriage and the backplate. Now these two together act as a housing for the cam lockers and the cam locking tabs, which kind of facilitate the movement for the locking motion. The carriage itself didn't go through much revision from last semester. One thing that did happen was the arms for the bridge bar were extended a little bit to help fit the cams. The backplate, on the other hand, went through quite a bit of revision. The backplate on the left sat flush with the carriage, and was mostly to help the cam lockers stay in place, stay straight with everything. What we moved to was a longer version of that, which swept around the side of the carriage, and this was to help also keep the locker straight and make it possible to place a standardized whammy bar on there. Placing any whammy bar on the carriage itself would have been a real pain. And finally, we have the cam locking and cam locking tabs. This is a cylindrical piece which will push into the back of the cam when it's in the locked position. This will help add another level of customization for any guitar player. Not only can the player bend multiple strings, they can also pick which strings they want to bend. The piece itself went through a lot of revision initially. It started out as a pen-like clicking system, which proved to be a little bit more difficult than we needed. So we moved to this sliding system. And at the end of last semester, on the left, and the current version on the right, they're pretty similar. The only difference is the piece was made longer, the hole was moved up, and the flat spot on top is a little bit larger for machining purposes. And currently at this point, the can locking nut is just a simple screw for simplicity.
Okay, so over the course of the semester, we had to make a few design compromises to meet our goals. So what's currently on the guitar is what's pictured, and it's a simplified version of what we were showing you earlier. We've taken out the string selection, and the reason we had to do that is because there was a lot of the springs in the system were binding, because they had a very small area. The cams tilt, and the strings they're compression strings, they're made to go straight up and down. And so what we would have had to have done, given more time, was extend those cams farther out, and that would improve the spring geometry, allowing us to do the string selection. Also, we used a standardized mounting plate, and that caused us to do a lot of routing on the guitar. And so if we would have had more time, we could have designed our own mounting plate and not had to do so much routing.
All right, so in order to show you guys that this test actually works, we had to find some way to translate the data. So this is a PC electric bridge which goes on the bottom of the guitar. Strings run over each one of these saddles, and there's a wire that comes out of each one of them. So when string vibrates, the PC electric sensor translates the vibration into voltage, and that sends it through the DAC, which is the National Instruments 9205, that's then hooked up to the laptop, which is then the block diagram for our program. The DAC assistant runs through the filter. Each string has a separate filter and spectral instrument and signal select. So this filter, it gets rid of the ranges of frequencies that we don't want for each specific string. Spectral measurements then takes sine waves from that information and translates it so that we can get a graph of amplitude versus frequency. And the signal select is simply just to pick each specific channel.
So now we're going to show you the actual live lab view output. We're going to show you what our testing looks like.
You do the high E, you can see the little E down there.
Okay. All right, live demonstrations, fun stuff. Well, let's show them So when that was working yesterday, we took some screenshots of us bending a chord up or down, and Cedric will tell you about that.
All right, so here are the frequencies, each one for each specific string. Start with the low E up here and goes all the way down to the high E up here to the low E. So here we have the frequency with the peak is where we're measuring the results that we get. So here is full step down, and each one of these represents that for each string. This is going a full step up. So here we have a chart for, this is standard tuning that we have. It was holding an E chord, and this is the chord, these are the notes that should be presented on the graph. So as you can see from the full step up, most of the numbers are pretty accurate to what we wanted them to be. They're slightly off a little bit because there's a difference in cents, which again, the cents is a half step, 100 cents is a half step, and these are all measured in steps.
So the important numbers to look at on the screen are the ones in green, and that's the correct and difference column. So that's the difference in cents from the ideal when we bend that E chord a step up on the top and a step down on the bottom. Now you can see that some of these are a bit more off than we'd like. Some discrepancies that came with our testing, we're using kind of a cheaper guitar, and the tuners aren't the best. So as you're bending, they can let go a little bit and throw off your tests. Also, there's some binding at the nut near the tuners where the strings are held up at the neck. And so with some improved guitar equipment, we could have improved the accuracy of these tests. But still, even with that, you can see that, like the G string, for example, if you follow that over, that's 15 cents off. Bent bending a step up, and 44 cents off bending a step down. Now that's pretty significant, and you're going to hear that. And that would suggest negative 15 and plus 44 would suggest that we would size that diameter of that cam up. And so using this data, we could correct the cam diameters in the next revision. But all these are numbers, and I think it'd give you a much better idea if you actually heard it. So the amp set up for you, and I'm going to bend a cord, and you can hear how that cord moves up and down. So this is a D chord. And that's an E. And that's a C. It's a little bit out of tune because I pulled it out of tune because of the tuners, but you can hear that D move up to the E pretty smoothly.
So there are many difficulties associated with manufacturing such small parts. Our designs called for some extremely high tolerances, which meant that some parts had to be CNC'd. And in addition, there were only 2 mills in the student machine shop that were equipped with digital readouts needed to attain that accuracy. Throughout the process, we really learned the differences between stainless steel and aluminum. Not only is stainless steel more expensive, but much more time-intensive and difficult to manufacture. Jigging and work-holding procedures led to some unanticipated difficulties. For instance, some of our parts were too small to fit in the vices on the mill, even when using the largest set of parallels. And in other instances, dimensions of some parts had to be left large in order to allow clamping into the workpieces. And in that sense, the order of operations became a bit unintuitive when considering jigging. Some of the parts that could have been designed differently, as we mentioned, are the cams in the carriage. As previously mentioned, the cams needed to be a little bit longer to alleviate the spring binding problem that prevented us from showing our original design here today. And we could have allowed ourselves a little bit of design freedom and avoided some machining headaches had we made the carriage a little bit taller. And finally, the machining process really solidified our understanding of the concepts of design for manufacturability and design for assembly. So moving on to some of the challenges that the team overcame during the process. First off, it's really easy to design a part in SolidWorks that is overly difficult or even impossible to machine. As an example, our carriage, we spec'd out some number 0 tap holes centered on a wall thickness of only 1/10 of an inch, which looks fine on the computer screen, but you don't really grasp how small that is until the part is actually in your hand.
Time constraints for us is probably one of our key challenges. That kind of incorporates a lot of our other challenges. Availability of the shop is one of them. I'm sure we all wish we had more time in the shop. And in the beginning of the semester, availability of machines was also a problem. And just random delays that were contributed due to our other challenges, such as mistakes and breakage, which led to increase in costs and decrease in efficiency. Another one would be miscommunications. For example, we use a larger tab size hole because we had to, and I forgot to tell you that we should probably change that for something. Redesigning and machining concurrently throughout the entire project was also a challenge. It was definitely a lot easier learning it in 138 than actually doing it. You can imagine like all these challenges just being stressful, especially if you experience them either at least one or all of them on many, many days. But definitely we got through it, and definitely we couldn't do it without our knowledgeable advisors. And we is why we'd like to give special thanks to Coach Coleman, Nick, Mike Noon, Coach Sprott, and Rustin. And that's our presentation. Any questions?
So with that system, does it only work on one specific chord before we have to reset the cams? Or
No, that'll work anywhere all up and down the neck. It'll always send the strings in the same musical interval. So you get any chord shape anywhere on the neck.
And would that still apply if you don't use standard tuning? Or would you have to adjust it?
Yes, that would be the same. You don't use standard tuning.
Assuming you had a really nice guitar with tuners that held really well, even like the nicest available.
Yeah.
Over time, did you guys do any calculations on the slip even with a nice tuner from constantly going back and forth?
We didn't do those calculations. I mean, ostensibly you could tune in between songs, or the type of bridge that we base ours on is kind of notorious for tuning issues. So in the future we work on that.
Yeah, ideally, we have like more of a floor set up and have like the tuning blocks at the top of the neck, and that'll keep the string in place.
Yes.
This is a small thing. I just noticed that there was a little bit more error when you were trying to bring the chord down rather than bringing it up. Do you guys have any thoughts into why that was, or do you think it was just the manufacturer maybe, or?
My theory was that it was binding at the nut. The way the nut's designed, it has one side of it where the strings go through that's kind of a hard 90-degree angle, and the other side is sort of this smooth roll-off. And so we probably could have done some. That's important to keep the intonation correct, that hard 90-degree angle. But if we have some sort of like locking nut that clamps the strings there, we could have eliminated that issue. Professor Marwa?
Yeah, I was just wondering sort of the limitations of where you could take this. Could you basically create like a player guitar or something where you could program it to go through and change the chords accordingly, or?
Yeah, you'd have to do something with the tuning also, because if nobody touches this guitar and you bend this bar and strum it, it doesn't sound good. If you were in an open tuning maybe, which is like when you strum the guitar with no hands on it, it'll play a chord. You could bend some chords, but you'd be pretty limited because a lot of chord progressions have major and minor chords in them, which involves changing the shape. If you coupled this with some sort of robotic tuning thing, you could probably do something.
So each cam is made for like each specific string, width, and I don't know if I'm talking about guitar strings, but are there like different widths even for, I know, 6 strings, 6 different, but is there different widths even for, below string, or?
Yeah, different guitarists use different strings, anywhere from 8s to 13s. That's how they specify the high E. So there's a wide range of strings that you can use, and you have to get a different cam for each string. Yeah, the diameter that string needs is its mass and diameter.
Did you find your testing and analysis that the rack string and core strings had a consistent error? Was there some consistency of a solid string versus rack string that fail or into the ship?
One interesting thing that we noticed between the wound and unwound strings is that you needed the largest diameter wound string required very little movement, and the largest diameter unwound string required very little movement, but their diameters are much different. The largest unwound string is like 20.023 inches, and the wound string is 0.046. So that was one interesting difference that we noticed. We haven't done the analysis as far as if we could extrapolate our data and figure out the diameters for all the strings or something. I think that's kind of where your question was headed. But that would be an interesting analysis that we could do for sure. Joe?
So when are you going to file with that?
I've already started looking into it. Yes?
Do you think that your tolerances and stuff like that on your cams, if you could have held the tighter tolerances on those, that would affect your airs that you're
CNC,
Ah.
and we try to get as tight a tolerance as possible. I calculated out that a tolerance of tenths of thousandths might affect it, and that's just purely theoretical. In the real world, thousandths probably would be sufficient and is sufficient, especially with the way we got these original diameters was not that accurate, and so we would need a better way to obtain these original diameters. But now that we have something on paper in this data, we can actually use these cams in the next iteration, improve the
Good, thank you.